Millions of barrels of crude oil cross the world's oceans every single day. To carry it, companies build gigantic oil tankers that can stretch for nearly half a kilometer, transporting so much oil that it would take thousands of fuel trucks to carry the same amount. At first glance, you might think there would be a faster way. Why not transport oil by airplane? After all, an aircraft can deliver cargo in just a few hours, while an oil tanker may take weeks to cross an ocean. But nobody does it. Every takeoff with such a massive load would require enormous amounts of fuel. The transportation cost would become so high that the price of oil would skyrocket before it even reached the refinery. But that's not even the biggest problem. How do ships safely move millions of tons of highly flammable cargo across the oceans? And is there ever a situation where transporting oil by air actually makes financial sense? Today, we're going to discover why almost all of the world's oil travels by sea, and how gigantic oil tankers help make the modern global economy possible. And by the end, you'll find out exactly how expensive a normal car refueling could become if crude oil were actually transported by airplane.
Back in the 19th century, people began extracting oil in enormous quantities. At first, crude oil was stored in ordinary wooden barrels. Each barrel held roughly 150 liters and was sealed tightly with a wooden plug. The barrels were loaded onto horse-drawn wagons and transported to the nearest railway station. There, they were transferred onto ordinary train cars. The trains carried the cargo to cities and ports. Then came the most dangerous part. At the port, the barrels were loaded onto ships and stacked on top of one another inside dark cargo holds. These ships were often made of wood and powered by sails. And this transportation system created enormous problems. During storms, the barrels constantly slammed into one another. The wood dried out in the heat and cracked in the cold. Oil leaked onto the floors of the cargo holds. The wooden boards of the ships became soaked with highly flammable liquid. And all it took was a single accidental spark from a kitchen stove or an oil lantern to start a devastating fire. In the middle of the ocean, entire ships could be consumed by flames within minutes. On a single voyage, a ship could lose up to half of its cargo through leaks alone. For the owners, the financial losses were enormous. Something had to change. In 1878, Swedish engineers Ludwig and Robert Nobel decided to completely rethink the system. The brothers were working in the oil fields around Baku, and they quickly realized that transporting oil in barrels was both expensive and extremely dangerous. So they decided to build a ship where the vessel itself would function as a giant container. The result was the Zoroaster, one of the world's first successful dedicated oil tankers. Its hull was constructed from strong iron plates. Inside, engineers created large metal compartments designed to hold liquid cargo. Instead of loading hundreds or thousands of individual barrels, crude oil could now be pumped directly into these tanks through pipelines. The ship was powered by a steam engine and began transporting fuel across the Caspian Sea. The results were immediate. Transportation costs dropped dramatically. Oil no longer leaked from thousands of individual barrels, and the risk of fire was greatly reduced. Shipbuilders around the world quickly began copying the concept. The age of the oil tanker had begun. But by the middle of the 20th century, the industry faced another major problem. In 1956, Egypt closed the Suez Canal. The canal had been one of the most important shortcuts connecting Asia with Europe. Without it, many tankers could no longer use the shortest route. Instead, they had to sail all the way around Africa. The journey became thousands of kilometers longer, and travel times increased dramatically. Transporting oil in small ships over such enormous distances became incredibly expensive. So, engineers came up with a simple solution. They started building much larger ships. And that's how the era of the supertanker began. One of the largest ever built was the Seawise Giant. Constructed in Japan, this enormous vessel measured approximately 458 meters in length. If you stood it vertically, it would be taller than some of the world's largest skyscrapers. Its beam was nearly 69 meters wide enough to fit several football fields side by side. When fully loaded, the ship weighed more than 500,000 tons. Because of its enormous size and draft, it couldn't pass through shallow waterways such as the English Channel or the Suez Canal. And after shutting down its engines, it needed several kilometers to come to a complete stop. Yet this giant proved something important. One enormous tanker could carry as much cargo as an entire fleet of smaller ships. By the middle of the 20th century, the world's oceans had become dominated by these floating giants. But here's the real question. Humanity has built enormous passenger aircraft and some of the world's largest cargo planes, so why do we still move millions of tons of black gold across the oceans by water instead of delivering it through the sky in just a few hours? The answer becomes obvious when we look at the mathematics. Let's compare a massive cargo aircraft with an ordinary modern oil tanker. A heavy cargo aircraft can carry an enormous amount of freight, but even the largest aircraft are limited by the amount of weight they can safely lift. Now compare that with a medium-sized modern oil tanker. A single tanker can carry hundreds of thousands of tons of crude oil. That's millions of barrels.
If you filled standard tanker trucks with the same amount of oil and lined them up on a road, the line could stretch for hundreds of kilometers. To transport the same volume by air, you'd need hundreds or even thousands of cargo flights. And that's where the problem becomes obvious. The economics simply don't work.
Now we come to pure physics. Crude oil is heavy. A liter of oil weighs close to a kilogram. To lift an airplane carrying hundreds of tons of this dense liquid into the sky, its engines have to burn enormous amounts of aviation fuel. And here's the strange part. That aviation fuel is itself produced from crude oil. So you would be using expensive fuel made from oil to fly a relatively small amount of crude oil across the planet. From an economic perspective, the entire process makes very little sense. A tanker works completely differently. This is where a principle many of us learned in school comes into play, Archimedes' principle. As the tanker is loaded with hundreds of thousands of tons of oil, it becomes heavier and sinks deeper into the water. But the water pushes upward against the hull, supporting the enormous weight of the ship and its cargo. The tanker doesn't have to lift its cargo 11 kilometers into the sky. Its engine simply turns a massive propeller that pushes the ship forward through the water. The vessel accelerates slowly and continues moving across the ocean. For every kilogram of cargo, a tanker can consume dramatically less fuel than an aircraft. The ship mainly pays the energy cost of moving forward, not the enormous energy cost of fighting gravity. And that's the fundamental reason why the sea dominates global oil transportation.
This efficiency comes with a serious responsibility. When millions of barrels of oil are involved, a single navigation error can create consequences that last for decades. In 1989, one of the most infamous oil tanker disasters occurred in Alaska. The American tanker Exxon Valdez struck a reef near the coastline. The impact damaged the hull, creating a massive breach. Tens of thousands of tons of crude oil spilled into the surrounding waters. The oil spread across hundreds of kilometers of coastline, creating one of the most devastating environmental disasters in modern history. The disaster forced governments and shipping companies around the world to rethink tanker safety. New and stricter construction standards were introduced, and the era of the double-hulled oil tanker became the new standard.
In the past, a single layer of steel separated the oil from the ocean. Modern tankers use two layers. One steel hull sits inside another. Between the outer hull and the internal cargo tanks is an empty protective space. If the ship strikes a reef or collides with another vessel, the outer hull can absorb the impact, while the inner cargo tanks remain intact. Water may enter the outer section, but the oil remains contained. The same spaces can also be used as ballast tanks. When the tanker returns without cargo, seawater can be pumped into special compartments to keep the ship stable and prevent it from rolling dangerously in heavy waves. But one of the most dangerous moments actually comes when the tanker is being unloaded. Once the oil is pumped out, the cargo tanks are left mostly empty. A thin layer of oil remains on the surfaces. As it evaporates, the empty tank can fill with highly flammable hydrocarbon vapors. A single spark could trigger a devastating explosion. Even dropping a metal tool onto a steel surface could potentially create enough ignition energy. So how do tankers prevent this? They use something called an inert gas system.
As crude oil is pumped out of the cargo tanks, an automated system immediately replaces the empty space with inert gas. This gas is produced using exhaust gases from the ship's main engine. The exhaust is cooled, cleaned, and processed until it contains very little oxygen. And without enough oxygen, combustion becomes almost impossible. Sensors constantly monitor the atmosphere inside the cargo tanks. The system keeps oxygen levels below a safe threshold. Under these conditions, even an ignition source cannot easily start a fire. This technology allows tanker crews to transport enormous quantities of highly flammable cargo across oceans with a much lower risk of explosions inside the ship. But even with all these safety systems, there are situations where transporting oil by air becomes necessary.
The first situation involves emergencies at offshore drilling platforms. Imagine a pipeline breaking at a remote oil well in the middle of the ocean. Crude oil begins pouring into the water. Every hour of delay can make the environmental disaster worse.
Waiting weeks for a large rescue vessel to arrive may simply not be an option. That's when heavy aircraft become extremely valuable. Aircraft can rapidly deliver specialized equipment, powerful pumps, containment booms, and chemicals used to control and treat oil spills. In some cases, engineers may also transport samples of the leaking crude oil to laboratories on the mainland. Scientists can quickly analyze the oil and determine which treatment methods will work best in the specific marine environment. In these situations, nobody cares about the cost of aviation fuel. The airplane is there to save time and potentially save an entire ecosystem.
The second situation involves the exploration of remote oil fields. Imagine searching for oil deep inside a remote forest or across a frozen polar landscape. There may be no roads, no cities, and no power lines for hundreds of kilometers. Workers arrive by helicopter and begin drilling. Then, several kilometers below the surface, they discover their first signs of crude oil. But before a company invests billions in pipelines, factories, and infrastructure, it needs to know exactly what kind of oil it has discovered. Samples are collected in specially designed metal containers. These samples are transported across rough terrain to the nearest temporary airstrip. From there, a light cargo aircraft can deliver them to a major city within a few hours. Laboratories analyze the samples for sulfur, paraffin, and other properties. They also determine how much gasoline and other valuable products can be produced from the crude. Without rapid air transportation, a major exploration project could be delayed for months.
The third situation involves specialized chemicals used during drilling operations. Crude oil deep underground can sometimes be extremely thick, almost like cold honey. Without the right additives, it can become difficult to move through pipelines and can damage pumps. Special chemical additives are used to improve the flow. But some of these chemicals are sensitive to heat or can separate if they spend too long in a ship's cargo hold. If a remote drilling platform suddenly runs out of these critical chemicals, production could stop almost immediately. In that situation, the company may charter a cargo aircraft, load it with the necessary chemicals, and fly them directly to the drilling site. An aircraft traveling at hundreds of kilometers per hour can save a company from enormous financial losses. So yes, oil can travel by air, but only when time is worth far more than money.
Despite their incredible efficiency, oil tankers have one major weakness. They are tied to the geography of the planet. Ships cannot simply fly over obstacles or change direction instantly. They must follow specific maritime routes. And along these routes are narrow straits and artificial canals. At some points, the available passage may be only a few hundred meters wide. If one major waterway becomes blocked, global oil transportation can be disrupted almost instantly. One of the clearest examples occurred in March 2021. The container ship Ever Given became stuck in the Suez Canal. The vessel was nearly 400 meters long. Strong winds pushed it sideways until its bow and stern became wedged across the canal. The ship effectively became a giant wall of steel. Within hours, hundreds of vessels were trapped on both sides. Among them were fully loaded oil tankers carrying millions of barrels of crude. Their engines were shut down. The crews could do nothing but wait. Rescue teams brought in heavy excavators and worked around the clock, digging sand from beneath the stranded vessel. Powerful tugboats pulled the ship in different directions using enormous steel cables. The operation lasted for days. During that time, supply chains were disrupted and markets around the world became increasingly nervous. The incident demonstrated just how dependent global trade is on a handful of narrow maritime choke points.
Another critical location is the Strait of Hormuz, near the coast of Iran. A huge portion of the world's seaborne oil trade passes through this narrow waterway every day. The safe navigation channels are only a few kilometers wide. If shipping through the strait is disrupted because of geopolitical instability, or if a tanker suffers a serious navigation accident, the consequences could spread around the world. Oil companies cannot simply redirect their tankers overnight. Ships may have to turn around and travel thousands of additional kilometers around Africa. That means extra weeks at sea and thousands of tons of additional fuel consumption. This reveals the strange paradox of giant oil tankers. Their enormous size is both their greatest strength and their greatest weakness. They can move colossal quantities of oil across oceans at incredibly low cost. But if a small piece of land, a narrow canal, or a sandbank gets in their way, they can become almost completely helpless. Aircraft can simply fly over obstacles. They can change direction within minutes. They can land at another airport. Tankers don't have that freedom. They are permanently tied to the narrow waterways of our planet.
Now let's put all the numbers together and calculate what oil transportation really means for the price of fuel. When crude oil is transported by sea, the transportation cost is surprisingly small. A giant tanker may burn a huge amount of fuel during an ocean crossing, but when that fuel consumption is divided across millions of barrels of crude oil, the cost added to each liter becomes tiny. That's why maritime transportation helps keep fuel affordable. Now let's completely change the system. Imagine that all crude oil had to be transported by aircraft. Consider a normal family car with a 50-liter fuel tank. To produce the gasoline needed to fill that tank, a refinery requires a larger amount of crude oil as feedstock. Now imagine that this crude oil has to be flown halfway around the world in heavy cargo aircraft. The enormous amount of aviation fuel required and the strict limits on aircraft weight would make the entire process dramatically more expensive. If crude oil were transported exclusively by air, the cost of the raw material could increase many times over before it even reached the refinery. The cost of refining and distributing the final fuel would rise as well. And eventually, the driver would feel the impact directly. Instead of paying a relatively affordable price for a liter of gasoline, drivers could face prices several times higher. A normal full tank could become an enormous financial burden. And the consequences wouldn't stop at the gas station. Food prices would rise because delivery trucks would also need expensive fuel. Public transportation would become more expensive. Air travel would become even more costly. The entire global economy would feel the shock.
And that's exactly why crude oil is almost never transported by air. The enormous oil tankers crossing the oceans may look slow and outdated compared with modern aircraft, but in reality, they are one of the most important pieces of infrastructure supporting the modern world. They move millions of barrels of crude oil between continents, quietly and continuously, following the laws of physics and the brutal mathematics of economics. Airplanes are perfect for transporting people, urgent cargo, medical supplies, and emergency equipment. But when it comes to moving millions of tons of dense, heavy crude oil, nothing can compete with a giant steel ship floating on water. Those massive tankers are the invisible machines that keep the global economy moving. And every time you fill your car with gasoline, there's a good chance that somewhere along the journey, that fuel began its life inside one of these enormous giants of the sea.
Think about what happens the next time you stop at a gas station. You pull up, insert the nozzle, and fill your tank. The entire process takes only a few minutes. But the journey that made that fuel possible may have started thousands of kilometers away. Deep underground, crude oil was extracted from the earth. It was then transported through pipelines to a coastal terminal, pumped into a massive tanker, and carried across an ocean. After reaching its destination, the crude was unloaded and transported to a refinery. There, enormous industrial machines heated and separated it into gasoline, diesel, jet fuel, and countless other products. The gasoline was then loaded onto another tanker truck and delivered to a local fuel station. By the time it reaches your car, the oil has already passed through an incredibly complex global network. And at the center of that network is the humble oil tanker. It may move slowly, it may take weeks to reach its destination, but its incredible capacity makes the entire system possible.
The economics of shipping are surprisingly simple. The larger the vessel, the more cargo it can carry on a single voyage. And when the cost of fuel, crew, maintenance, and navigation is divided across millions of barrels, the transportation cost per barrel becomes extremely small. That's why shipping companies have always had a strong incentive to build larger and larger vessels. But there is a limit. A tanker can become so large that it can no longer enter important ports or pass through critical canals. At that point, making the ship even bigger stops being an advantage. The solution is to build specialized terminals capable of handling enormous vessels. Deepwater ports are constructed far from shore. Long pipelines connect these terminals to inland refineries. The tanker arrives offshore, unloads its cargo, and then disappears back into the ocean. In this way, the entire global oil industry has evolved around the capabilities and limitations of these gigantic ships.
A modern supertanker is more than just a giant container. Inside the steel hull is an incredibly complex system of pumps, pipelines, valves, sensors, and safety equipment. The cargo is divided among multiple tanks rather than stored in one enormous compartment. This helps control the ship's balance and reduces the movement of liquid inside the vessel. Because crude oil can shift from one side to another as the ship moves through waves, managing the cargo is a critical part of navigation. The crew constantly monitors the ship's weight distribution, fuel levels, ballast tanks, engine performance, and weather conditions. On the bridge, navigation systems track the vessel's exact position. Radar watches for nearby ships. Satellite systems provide global positioning. And automated alarms warn the crew about dangerous changes in pressure, temperature, or tank conditions. From the outside, a tanker may appear to be nothing more than a giant steel box floating across the ocean. But inside, it's a carefully controlled industrial machine operating around the clock.
And perhaps that's the most fascinating thing about oil tankers. They rarely attract attention. You don't see them flying overhead. You don't hear them racing through cities. Most of the time, they're thousands of kilometers away, slowly crossing the ocean. But their influence reaches almost every person on Earth. The fuel in your car, the electricity used by factories, the plastic products in your home, the trucks delivering food to supermarkets, the airplanes carrying passengers across continents. All of these industries depend, directly or indirectly, on the enormous global flow of energy. And much of that energy is carried across the world's oceans by these gigantic steel vessels. So the next time you see a massive tanker disappearing over the horizon, remember what you're actually looking at. It's not just a ship.